Welcome back to the seminar. It's my great pleasure to introduce Rui Lu, who is a first-year graduate student advised by Professor Huang in the Department of Automation at Tsinghua University. His research interests are broadly in machine learning, such as computer vision, reinforcement learning, robustness, and theoretical understanding of deep learning. And prior to his graduate study, he received a bachelor's degree in Yao class at Tsinghua University. So Rui, the stage is yours.
Okay, thank you very much for your introduction. And I'm really privileged to be invited to give this talk to you, introducing our latest work. So today's topic is on the power of multitask representation learning in Linear MDP. And this is the collaborative work between me and Professor Simon Du in University of Washington. So let's get started. Let's start with a very basic concept in MDP. It's called the sample complexity. So it means the minimum number of samples to learn a near optimal policy. But the problem is that usually it is too large. So because, for example, like this is a regret bound for learning a tabular MDP with a generative model. So generative model means you can query the state action and get the reward and one sample of next state for arbitrary state action pair. And if you want this regret to be epsilon, then the required number of samples is of this order. But it is proportional to the cardinality of the state space and action space. And the problem is too large in practical problems. For example, a 19 by 19 Go game has over 10 to the power 360 number of possible states. So it is even more than the number of atoms in this universe. So this makes learning very intractable. So how to solve this problem? People have come up with many clever ideas. So one of them is to learn a good representation. So what is a representation in MDP means? So I will use the figure on the right as an example. It is a very famous game several years ago called Flappy Bird. So the player has to tap the screen and let this bird fly through the narrow gaps between the tunnels. And if you send this image snapshot of this video game to your agent, the raw state space, the dimensionality is the dimension of this image, and it's quite large. But actually, to solve this MDP, you only need to care about three real numbers, which is this x, y, and h, your relative position to the gap, and your height. So this means that although the original raw input dimension is quite large, but what you need to solve this MDP is just three numbers. It's a very compact representation. So this motivates people to first use some methods like autoencoders or variation autoencoders to first do a reconstruction task. And then you get a compact representation at the bottleneck. So you use the output of the autoencoder as the code. Then you treat this code as the new state. And you learn MDP on top of this compact code. And this has proved to be have a very good efficiency at reducing the sample complexity. There are also many other sophisticated methods to use representation and to use them to reduce the sample complexity. I just list several typical papers here. So although we know empirically learning a good representation usually helps to reduce the sample complexity, but the theoretical understanding for why it works, when does it work, and how it works is still limited. So basically, our work hopes to answer these two questions. So first question is, under what condition do we know that an empirically good representation is guaranteed to reduce sample complexity in a novel environment? And if it does, to what extent? And second question is, can we give some statistical explanation and get a theoretical insight about how multitask representation learning helps to reduce sample complexity? Okay, so then I will briefly introduce some background information just to tell you what the notations I'm using. So first is Finite-Horizon MDP. It is just a special class of MDP. So which means the total numbers of interactions between agent and environment is finite. You just repeat this same action and get reward for capital H times. And this capital H is called the planning horizon. And the goal for an agent is to learn a good policy. A policy is a mapping from state, action to action space. Then you hope to maximize the cumulative value. And maximize this cumulative value is equivalent to minimizing the gap between the policy's value to the optimal policy's value. Okay, so I think this is quite common and everybody knows it. And this is the part that I want to introduce because in the standard MDP definition, there's nothing about the representation. So we need a model, a theoretical model, to characterize the role of representation function in solving MDP. So that's why we solve the linear MDP. We try to discuss and analyze this special class of MDP. So a linear MDP is an MDP such that it permits a special feature embedding function phi. This function phi takes state and one action as input and outputs a d-dimensional vector. So what is special about this d-dimensional vector? So it also assumes that there exists a constant vector theta. So if you want to know the reward of certain state and action, you just take the dot product between this phi SA, this representation, and theta. And also, if you want to know the transition dynamics, you can take the dot product between this phi SA and another function psi. For example, you want to know what is the probability for me to get to S prime if I perform action A at state S, then you just take the dot product between phi SA and psi S prime. So basically, this d-dimensional vector output by the function phi contains all the information that you need to solve this MDP. So this characterizes what a good representation in linear MDP means. And usually without the laws of generality, we normalize this representation function. So we can assume that the output of this representation function is constant bounded for arbitrary state and action pair. Another important property for linear MDP is that since the transition dynamics and the reward are all linear in this phi SA, so we know any policy's Q value can be parameterized by a constant weight vector W. So this can be ratified through the formula on the right. So you just write out the definition of the Q value. So first part is the reward, and then it's the Bellman operator for the value of the next state. And since we know the reward is linear in phi SA, and the transition dynamics is linear in phi SA too, so you can extract this common term, and all the rest part is a constant vector. So which means if you know an MDP is a linear MDP, then to learn a good policy, or you want to learn a good Q value estimation function, you just need to learn a constant vector. And this property is regardless of what value function of the next state h plus 1 is. Okay, so any question yet?
You're good, I think.
Okay. So then let me introduce.
There is some question. Wait.
Okay.
From Guggen in the audience, he asked, do we know phi or psi?
This is phi.
Yeah. Do we know that? Like.
Yeah. That's a good problem. That's a good question. So most of the work in linear MDP assumes that the agent knows this phi. Most of the work assume that the agent knows this phi, and then they use this phi to learn. Yeah, but so this is a special point for our work because. Okay.
How about psi?
Psi. Psi is unknown. Psi is unknown because if you know phi and you know psi, it means that you totally know everything about this transition dynamics, right?
Okay. All right.
But in our work, one special point is that we do not assume that the agent knows this phi. So we want this agent to learn this phi by optimization, and our work is exactly talking about whether an empirically good representation phi learned from samples has the property to reduce the sample complexity in the new task.
All right,
Okay.
thank you.
You're welcome. Okay, so then we're good to go. And here's multitask training. So multitask training means that we train the agent to solve multiple tasks simultaneously. So here is the very famous game called Snake. You control the snake to get food everywhere. So each time when new food is put in someone else, it is actually a new task. So what is important about the multitask training is that usually all these tasks should share the same state action space. So for example, it's already snake, and the space that you can move is already square, and the action space is just 4 directions. They're all the same. And more importantly is the representation function for all these tasks. If they are all linear MDP tasks, then each task, all these tasks should share the same representation. So if so, when you train the agent to solve all these multiple tasks simultaneously, then it is believed that this agent can learn what a good representation is from all these different tasks. Of course, maybe each individual task emphasizes some aspect of what a good representation should be. And then you learn a common low-dimensional representation, which is utilizing all the data and the experience you learn from each task. And here is our learning framework. I will explain it line by line. So first, you initialize the value function to be 0. And then here is the multitask part. Eta is a distribution supported on various linear MDP tasks. So for example, this or snake task, and this is a supporting set for this eta, and you just sample some task, you sample some food position. And all these tasks share the same state space, action space, and that's representation function phi. And then to solve each task, you construct a distribution, and you sample some state action pair from this distribution. And after you get a bunch of state action pair, you query a generative model. We assume that we use a generative model in our work. And you use this model to simulate what is the reward of the state action pair that I just sampled from this distribution, and you get a next state sample from the transition dynamics. And then you just construct your Q value label by its definition. So first you get the reward from the generative model, and here you use the VH+1. So the next state's value is the value of the next state. You just used approximation of your own value estimation function from the level H+1. So that is why the for loop for this H is in reverse order. So each time when you want to know what is the Q value of level H, and then you can use the value estimation function just a level before that, which is H+1. And then after you construct this Q learning label, and you do this optimization procedure. So you do a bi-level optimization on those phi, this representation function, and W. And so you can see here, this phi SA and the dot product between W is your estimation for Q value. And this is the target Q value that you learned from the samples. And then you want to get an empirically best representation and vector W to minimize this error. And then you use this phi and W to construct the value estimation at this level. So you get prepared for the next level's Q learning at line 9. Okay, so this evidence is important. I hope everyone is good to go. Any questions?
Yeah, actually, I have a bunch of questions here.
Okay,
So the simplest one is regarding the setting. So when you say that the new task is sampled from this distribution nu or eta, so then everything is state space, action space, and the feature map is fixed. But then the transition function changes, and the reward function may also change. Because I guess in the snake example, it's only the reward that is changing, and not necessarily the transition dynamics.
Transition dynamics can also change because
I see.
because let me go back to this definition. Because I just assume all these tasks share this phi, but they may have individual psi.
Right. So psi and theta may be different between tasks.
Yeah.
All right.
Yeah.
Okay. So that was the easy question that I had. Then another one, which should be this step of constructing DT for task mu t. I guess this is going to be like the most difficult and tricky part in the algorithm design. So is this going to be getting a policy and running it in the environment, or is it going to be something trickier?
Yeah, you're right. This so in general, how to construct a good distribution here is difficult. Actually, Huang has a recent paper talking about this. But in our analysis, so I will introduce the first part is the linear representation class. It is a very you can construct the distribution very easily. You can just construct a uniform distribution over the standard basis, and that would automatically have a guarantee on the performance of your linear representation. But for general representation class phi, yes, you're right. Construct this distribution D is difficult. But in our final regret bound, there is one important parameter which is related to this distribution, measures how good this distribution is.
Right. Okay. And then the final question that I have is probably the most important clarification, which is when you say that you're minimizing both with respect to W and phi. Okay. So what is the size of phi then?
What do you mean by the size of phi?
So phi can be basically represented by a matrix that is of size SA times D. So are you really optimizing over that crazy set, or only over the states that are observed?
Let me see. So actually, this phi is a kind of is optimized within a function class. So you find
I see.
A best phi within some function class. For example, this phi can be linear. Then basically you're finding a matrix. Or if phi is a neural network before the final linear layer, then this optimization is just optimizing the neural network.
I see. But if it's let's say that it's a linear phi and it can be represented by a matrix, but it's still a huge matrix. So then how can you optimize this effectively?
Yeah. So this is a good question. Actually, we assume we have a computational model to solve this, because what we care about in this work is not efficiency or whether you can solve it efficiently. So what we really interested about is this empirically best phi and W have some performance guarantee in a new target task. So we care about the generalization. But about how hard or what is the exactly method, how fast this algorithm is to efficiently solve this is not the main point, or it is an orthogonal problem to our work.
So can I ask a follow-up question about this?
Sure.
So I guess you could characterize maybe your work as saying that you consider this oracle efficient learning problem, where you have an oracle that solves this minimization problem, where let's say little phi belongs to capital phi, and then you'll be interested in like how the capacity of capital phi is going to influence the sample complexity of learning.
Sorry, actually, I don't quite get your question.
So maybe let's just like see the results and then we'll see that.
So you want to scroll back, or?
No, I think that. So I can repeat my question. It was just that like, so there is the computational aspect, but I guess you just say that you assume that you can do the minimization and you don't care about the computational efficiency of that. And there is the sample complexity question. or how precise representation you can learn. And there, it's going to depend on what class these potential feature maps belong to, right? Like if that is a big class, then we don't expect much success. So as Gergely was saying, if you don't have any restrictions on all the phi's, this would be like filling a matrix that has SA by D entries. And if S is huge, then this is a hopeless task. So you would need to make some assumptions about that this phi belongs to some more restricted class.
Yes. Actually, actually, in our work, we assume this, for example, linear representation class, this capital phi is an orthogonal matrix. So which means the lines of it, this D, small d, rows of this matrix are orthogonal to each other, and these greatly reduce the total space that you need to search. And actually, if it is really a linear class, what you want to do the regression problem is actually you don't need to really optimize the phi and optimize the W, because you can just optimize the product between here, because here it is X, B, for example, then matrix B, and you just optimize BW, and it's enough. It's just a capital D dimensional vector.
Why is it a vector? I said that that's just a number, the net product.
What do you mean? Why is what?
Oh, the phi transpose W. I said that you were saying that the phi transpose W is just like, this is an overcomplete problem, right? Like you have way too many variables for like how much data you have, or I don't know, like you could view it as a constraint satisfaction problem where all these errors should be 0, and then you had, I don't know, these n data points over the t, I don't know, steps, and so altogether you have n times d data points, n times t data points, and but you have, like, if S and A is big and D is big as well, then you have so many variables that you can satisfy all these constraints. You can just set this to be equal to 0 unless you're making some further restrictions. But I guess like we should just wait and then we'll get to that.
I will talk in detail about the linear representation class. Maybe your questions will be answered.
Yeah. I think
when I get there.
So there is a small typographical, or I don't know, question. There is a phi of upper index h on this slide and a phi without the upper index h. What is the difference there? Line 12. The line 12 has
12?
a phi. 12, yeah. Has a phi in it, and that has an index h.
Yes. Well, we learned a representation phi for each level.
But on line 11, I don't see. Okay. I see. For each h. Okay, the arg means output is the phi of h. So that's the solution of that. Okay.
Yes, that's the solution. That's the specific solution at level h.
Yeah.
Okay.
All right.
I guess I can continue.
Sure.
Okay, thank you. Thank you for your questions. Okay, so then when evaluate your learned representation on target task, the overall procedure is quite similar. So except for this detail, now you don't need to optimize the phi. You just get the phi from the algorithm 1, which is your learned empirically best phi at each level. And then you just optimize over this simple weight vector W. And then you get a totally new Q-value estimation by this phi hat SA and your learned W at each level H. And then you got a policy on the target task. And then what we want to know is how good is this learned policy on the target new task. Okay, so then we are going to talk about some basic assumptions that we used in our work. So the common assumptions is, so first we assume that the agent has a generated model, which means it can get the reward of any state action and sample one next state from the transition dynamics. And second is the bounded reward and noise, which means at each level, the reward is bounded by 1, and the noise of the reward is bounded by some parameter sigma. For deterministic task, the sigma is 0. And the third one is the bounded input space. So this may require some introduction. So in common, so people talk about the linear representation. Usually, the phi receives 2 input, 1 state and 1 action. To help to better analyze these things, so we assume that we have a vectorization procedure. So it takes the state and action pair and then pack it into a single vector. And now our function phi just take 1 single vector as input. And we assume that this packed input, this single vector, its norm is bounded by 1. So some may ask, what exactly is this vectorizing procedure? So for example, if the action space is discrete, you can just, for example, you have k different actions, then you can just create k different blocks. And if you perform certain action, you just put the state into the corresponding block, and all the other blocks you set it to be 0. And that is some kind of the vectorization procedure. Or if the action space is continuous, and you can just simply concate the state and action. Okay. And
sorry, so is that
okay.
2 norm?
2 norm.
Right. Okay.
2 norm.
Good.
And here is the maybe the most important assumption, and it is a little hard to understand. It is called the task regularity and diversity. Actually, we adopt this assumption from Simon's latest work called future learning while learning the representation provably. So it first used in supervised learning. Basically, let me put it in this way. So as you know, learning a Q value function for linear MDP is just equivalent to learning a constant vector W. So each task is parameterized by a simple weight W. So the first property that we require for the task is regularity. So which means all these W, they should be constant bounded. They should be regular without any strange outliers. For example, there's no task which have arbitrarily large or ridiculously large norm W. And second is the diversity. So to achieve the authentic multitask training, these W's for different tasks, they should be diverse. So what is diverse mean? So roughly speaking, they should spread evenly in the d-dimensional space. And this is characterized by the smallest singular value of the matrix if you just concate all them together. And this is actually quite, I think, makes sense, because if all these weight vectors are concentrated, or they just lie in a hyperplane instead of spread evenly in this space, then actually they are quite similar tasks, and their efficiency for reducing the sample complexity won't be so well. Any questions or assumptions?
Yeah, so what I'm not necessarily understanding here is that here your sequence of W's, they look like a deterministic sequence from 1 to capital T, even though in your setup you had these as random samples. Like all these mu T tasks, they were sampled randomly from eta. And then basically when you make this assumption, then you would need to make it in like a probabilistic sense, that with high probability, these eigenvalues are more bounded by something, whereas here you're making this with probability 1. You're saying that if these conditions hold, then your theorems are going to hold.
Yes, you're right. So task regularity doesn't require this high probability requirement, but maybe diversity is. But actually, in our experiment and in real practice, you don't you don't actually sample from get samples from that eta, but you just set what are these tasks, and this assumption basically is made on those samples. Given that samples, this sample task should satisfy this condition.
Oh yeah, okay. So this is rather a definition of a property.
Yes, the definition of the property.
Rather a definition than an assumption. Yeah.
Okay.
What?
Okay, good. Yeah.
Can I also
ask a question? So
okay.
The W and the phi are inversely related. If I scale up the phi, I can scale down the W. As we are learning the phi, if we are not making an assumption about the norms of these phi vectors, then I can always make it so that at least the norm assumption is satisfied and the other assumption is satisfied, because I can just, okay, so the first is an upper and lower bound. Okay, so it's a theta, right? So you say that W star TH is theta. So it's like big enough and not too small.
Yes.
So that's like a very peculiar assumption. Okay, so I can't, so that kind of fixes the scale of the phi to some degree. And then the second assumption somehow talks about that there is some sort of diversity. But all of this, of course, depends on the choice of phi still. So I guess
the norm of the output of the phi is constant bounded. So so actually it doesn't matter
so that's an assumption.
The linear MDP, we assume that the output of the
it's okay. So it's because
constant bounded.
Linear MDP, you make that part of the definition of the linear MDP.
Yes.
I see. Okay.
So there's no scaling issue.
Okay.
So basically the phi just output a constant bounded norm vector, and then the W is another constant norm. So you take the dot product, and it's approximately still this order.
So I guess Nan also has a question. Simon partially maybe answered it already. Nan, you have a microphone?
Yeah, I do. Yeah, I was just wondering because if you think about it, in the case if diversity is not satisfied, but all the W is exactly the same, right? But if you keep testing on the same W, like that should be an easy task. So I was just wondering, like, if W is more generally, if W is drawn from a ID distribution, and you further test on that same distribution, then it seems like diversity condition shouldn't be needed. So someone has some comment about drop that setting having worse sample complexity.
Yeah,
I don't know, like someone can give some
ID assumption or the tasks. It's a more it's an assumption made by Mauer's paper in the link I sent in the chat. So that one, actually, you cannot get the read we have if you only have the ID assumption over the tasks. So here, this diversity assumption actually does not really need ID, but really requires, it's more like a deterministic condition over the source tasks. So these two assumptions are like they do not imply each other, but I mean the final read will be different.
Right. I was also wondering, like, if there seems another way to relax this is, I guess I'm just thinking of like something like a linear regression, right? And you have a bad design matrix, but if you ask the sort of like the online learning question, like you can always learn without a problem, even if the feature vectors, the design matrix given to you by the nature is very bad, as long as you're realizable. And I think you guys are in a realizable setting, right? So what I'm saying is that you can imagine a setting where like W is an arbitrary sequence, maybe chosen obliviously by the nature, and you learn from the first several W's and then, I don't know, like test on the next W. seems like there you also don't need diversity, I would guess.
So here, essentially, because what we care is the next target task. And here, basically, the bound is for the kind of worst case target, next target task. That's why we need diversity. So if you,
Okay,
I mean,
right,
you're right that
yeah.
if you have additional assumption about source and target task, instead of a worst case target task, you have some more benign target task, then I think this assumption can be relaxed. It's more like a more fine-grained condition there.
Yeah, I see. Yeah.
Okay. Thanks, Simon. Gratefully. So, can I continue?
Sure.
Okay, thanks. So finally, we are ready to present our final result for linear representation class. So here, the capital phi becomes the sort of this function. So it is just a simply matrix, and capital D is the original input dimension, for example, the dimension of the image, and small d is the representation dimension. So you just take the multiplication for this matrix and your original input, and then you automatically get the dimensional representation. And this B is restricted to be orthogonal. So the columns of this B should be orthogonal to each other. And there are 3 more conditions to ensure that the algorithm can converge and have a good approximation rate. So first is that the number of tasks should be enough. So it should be at least more than 2. Two times the dimensionality of the representation. And second is the capital N is the number of samples to learn the representation, and it should be larger than these 2 terms. So this is a threshold. So actually, only when the capital N is larger than this threshold, all the following bound could hold. Otherwise, you just learn rubbish. And also, the required number of samples for target task depicted by this small n, it should be larger than this term. And here is a kappa. Kappa I will explain later. So if the representation class is this capital phi, and these 3 conditions are held, then we have the following regret bound holds with probability at least 1 minus delta. It is this one. So here is the optimal value, and here is your learned policies value, and it is controlled by constant times this thing. Okay, so I'm going to introduce kappa, but I guess maybe you guys have many questions here.
Yeah, what's capital N? I just got lost of it.
Capital N is here. So you sample capital N here. You sample capital N number of state action pairs from this distribution. That is the sample complexity for the training task.
I see.
And small n is the number of samples you used for the target task. Here.
Right, and this result is then, so the state action pairs there are sampled IID? It's mu distribution?
You mean the mu?
Right, that line, yeah.
You mean the task, where the tasks are sample IID?
No, the data.
I think it's like this curly D, this data distribution or the state action distribution.
This data distribution.
Yeah, like line 5, you say sample this from that.
Yes.
Like, how does it work? Is it IID?
Or I guess the question is, like, how does the choice of this DT impact the result that you were showing?
Yes, it is hidden in the kappa. Hidden is related to this DT.
I have a more basic question. Is that sampling IID? So what do you mean by sample? Usually you follow a policy or whatnot, like what setting are we in? Can we just like reset states to whatever and then?
set states to whatever. Yes.
Yeah,
but,
like a simulator setting, which generative model, or what is this? Line 5.
Line 5. Yes, it is basically just like a training task. So, for example, in linear cases, this d t+1 is just you choose each standard basis and you query the generative model, or you can choose a bunch of the possible states that you used for example, random policy or epsilon greedy, and that would gives you a certain distribution.
I see.
Where your samples are sampled from. Yeah, this is just a notation for that distribution that you get these state action pairs.
Okay, and you are going to explain what choices you have there and how that impacts the results next. Okay.
Okay, so then we are ready to explain what is this kappa. Wow. So as I told you before, the choice of the distribution affect the sample complexity, and it is here in this d t+1. So this kappa is closely related to this distribution. So what does this kappa means? In our work, we call it least activated feature abundance, or LAFA criterion. So you can understand this, you can get an intuition from in to out. So first, this is a covariant matrix for your representation, and sampled from this specific distribution. And so it depicts an ellipsoid, right? So the minimum eigenvalue of this ellipsoid means the shortest axis for this ellipsoid. So what is the shortest axis for this ellipsoid? It actually means you use this learned hat phi and you evaluate it in this new distribution. Which direction of the feature is least seen when you sample from this distribution? And which means, although your hat phi knows some feature is important, but maybe for this distribution, you just match this feature activated very rare. So then your required number of samples is still large. And the kappa has the very obvious lower bound, which is d, because it is the minimum eigenvalue, and this d eigenvalues, the sum of these eigenvalues is constant bounded. So the least eigenvalue should be at least 1 over d. So kappa should be at least omega d. Okay. Any questions? Maybe you guys.
So I'm not sure about what this phi hat is here. Is this the feature vector that you get after solving this least squares problem?
Hat phi means the empirically based representation you learned from training task.
Right, but then how can you make sure that this kappa is actually small? Because there seems to be some recursion here that if you fix d, right, that implies a certain choice of phi hat, but this is going to result in some kappa that can be pretty horrible, right? Then you can go back to the drawing board and say that I need another distribution dt, but that's going to give you another phi hat, and then again you end up with a terrible kappa. So can you have like a procedure that ensures that kappa is small?
Yes. Well, so first, this problem does not appear in linear class, because linear class, if you learn a good empirically based phi for all the standard bases, then automatically you know it will have good performance on all the input, and then this kappa just matters for this specific distribution dt+1, whether some of the features appears common enough for you to learn the weight vector for that specific entry. But for general class, we make assumptions on this function class phi and this distribution such that you have the generalization is guaranteed.
All right. Well, I'm not sure I fully understand everything, but I guess you can get back to this later.
Yes.
Let's let you go ahead for now.
Oh, I don't. Yeah, it's already.
No, don't worry about it. Yeah.
Okay.
Can I ask a clarification question?
Sure.
So if you fix phi hat, you could always find some distribution such that this lambda mean is 1/d, right? Yeah, sorry. Yeah, the lambda mean is 1/d, so the kappa is d, or something like that. Or like maybe a little bit larger, but like that's the scope of it, right? So this is just Kiefer-Wolfowitz theorem, optimal design.
Yes, actually, usually for a target task, maybe you can come up with some algorithms to reduce this phi, to control it to be more d. But if you don't know, we just put this kappa as the criterion. That's why we call it Loffa criterion. So it matters independent of how good your representation, your learning representation is. Your sample distribution for the target task is also important.
I see that we are constructing dt+1, that distribution. That's our choice, no?
Yes, that's a choice.
Okay.
That's a choice.
So then we could choose it such that this kappa is the smallest possible.
If you could, then of course you want to choose a better dt+1 to make kappa smaller.
And we know that there exists.
Yeah, but phi hat itself is a function of dt. So there's some recursion going on.
Is it?
No, t+1 is the target task. So phi hat has nothing to relate it to. To this.
Oh, I see.
I know you construct dt+1. So if you are not afraid of a huge compute, you can always achieve kappa to be at most d.
Yes, if you have a good representation and you can construct this distribution with respect to this specific hat phi, and that is actually adaptive sampling, and that will make your sample efficiency for the target task much smaller. You're right.
Okay.
But our work just want to point out the relation between your sample and distribution and the final sample complexity that you will suffer.
Mm-hmm.
Okay.
Okay.
So let's taste this bound. So first, you want to control the suboptimality to be sufficiently small, say epsilon. Then the required number of sample for your capital N, which means your required number of samples for linear representation, it should be at this order. And as you notice, the capital D square is here. So which means you really need a large number of N to learn good representation. And this is not surprising because you need to squeeze out the redundant information. You want to get a compact code. So you need very large number of the samples to know what directions is actually redundant and you don't need it. And once you set this entity to be that large and this part is already small, you have a good representation, then the needed samples for the target task is only this part. So first bullet you can see is we get rid of this capital D square. So as this example that I mentioned before, the capital D is the dimension for this image. So it could be up to several 100,000. But the small d, the compact representation, is just 3. So you can see the benefit for learning a good representation. Once you get this good representation for any new target task which share the same representation function, you get rid of this capital D square, and you only need to deal with this small d. And kappa, we will talk about it later. Any questions?
Yeah, Jack Zhang had a question. Maybe he can ask his question.
Yeah, hi, Harry. So
Hi.
I was just wondering if, because earlier you assumed that the phi function is basically a linear function, right? It's a giant matrix.
Yes. In this part, it's a linear matrix.
Right. So then that means I can view the whole problem as not a representation learning problem, but just a typical linear MDP with known feature, where that X itself is the feature.
What do you mean by the X itself is the feature?
So the X is of dimension capital D, right? And we know the transition and reward are also linear function of the X.
Sure. What do you mean by X? Which X are you talking about?
Oh, like yeah, in the previous slides when you define that your phi class, with those three conditions, yeah, that X, right? Phi of X. I guess X is the vectorization of SA pairs.
Yes, you're right.
Yeah. So X itself is already a feature, right? It's already a vector.
Yes, it is capital D dimension.
Yeah, so I was just wondering, like, if you just treat it as a linear MDP on X, what's the sample complexity of learning? If you just apply any
you're right.
MDP algorithm.
That is exactly what I'm going to talk about. So
okay, cool.
What we really want to compare is compare if you have a good representation and you learn a novel task, and compared with you learn a new task from scratch. For example, you just treat it as a three-dimensional regression MDP, right?
Perfect.
So yeah. And actually, this bound can be also used for estimating the sample complexity if you just treat it from scratch. So the tricky part is here. You just ignore this small n term and you set capital T to 1. So then the training procedure of our algorithm 1 is exactly what you are talking about. You just treat this capital D as the feature and you learn a regression problem. And then this T to be 1, and this is the required number of samples that you need to solve this task. As you can see, the capital D square is what you need. So that is quite large.
So you're saying basically you use the same number of samples that is required to solve a single task.
Yes.
So now you can solve all tasks, or or some target task. Okay, thank you.
Yes. Yeah, you're welcome. Thank you for your good question. Okay, so in ideal case, which means if your sampling distribution dt is good, and it covers almost all the possible features in the new task, which means you have a good kappa, then the kappa reach the lower bound as OD. So then you further reduce this bound to be d square h d square. So what's important about this is now the algorithm gets rid of the raw input dimension capital D. You no longer need to deal with the original high dimensional raw input. And actually this quite makes sense because now since you have a compact code and you just need to treat this compact d-dimensional vector and you don't need to know anything about the original d-dimensional input. So the summary, to make a summary, the takeaway conclusion is this. For linear representation function class, if the following conditions are held, then we know an empirically good representation is guaranteed to reduce sample complexity in target task. These conditions are first, all these training tasks and the target tasks, they should share this representation and the state space and action space. The second condition is that all these tasks should be regular and they should be diverse, so the usage of the data is efficient. And third condition is that the training data distribution has a well-bounded Laffer criterion, which means the feature coverage is good. Okay, any questions? No?
All right.
Okay, so we are good to go.
That's the end of your talk.
Or is it? No, actually, we still have. I've got faster.
Oh no! Sorry. That was just that sounded very much like a final conclusion, but not yet. No. Please go ahead.
Actually, my favorite part, which at last, we designed a special environment to corroborate our theoretical findings. It's quite interesting. So.
All right. Yeah. Let's do it. Yeah.
Okay. So we do it for the general representation class. We extend the analysis to general representation class. But something is different for this general representation class because, for example, in linear representation class, you set this dt to be the uniform distribution over the standard basis. Then automatically you have the generalization property on arbitrary input, but this is not guaranteed for general class phi. So to make general representation class work, we need to add several assumptions with which our algorithm can guarantee to reduce the sample complexity. So these are also the question, the question that we hope to answer. What is the condition that an empirically good representation could help to reduce the sample complexity? So these conditions are the learnability of this phi. So namely, with enough number of samples, it is guaranteed that your estimations converge, and generalization, which means by the finite set optimization, your learned phi has the generalization ability to all the possible input, and also the uniqueness of the representation. Because this is too technical and full of hand-waving math, so I won't introduce them in detail. If you are really interested, you can go to our full paper and to take a look at this. And the final result is like this. So it's quite similar to the result before, and you just focus on this, the capital N, and on the denominator, you can see this. This is a Gaussian width complexity measure for this function class phi. And for the target task, it is just kappa d. So now you can see that we get rid of this sample complexity by the factor of the complexity measure for this capital phi. And it is worthwhile to point out that in linear representation class, this Gaussian width complexity for phi is exactly capital D, and this reduced to our linear results. Okay, any questions?
Yeah, so can you explain kappa here? What is kappa?
Kappa here, it is just like before. This sigma q, the definition is exactly as this.
So the general linear representation learning means that the phi hat is going to be an all-linear function that comes from some learnable class, and then that's it.
Yes. Yes.
And other than that, we are still in the linear MDP case, blah, blah, blah. Okay.
Yes, but the definition for kappa is still. So,
yeah.
This is universal.
Okay.
This is universal.
Yeah. Okay.
Any more questions? Okay.
No.
Okay, thank you. And finally, I'm going to introduce this very interesting experiment for our theoretical finding. So we design a Gridworld environment. So as you know, Gridworld is just an agent is traveling in these cells, and you try to go to the destination with a positive reward and try to avoid the places with negative reward, and each step costs you some reward. The interesting part for Gridworld is that when you take the action, for example, up, and with some probability, your actual action is shifted to left. And actually, this is a quite simple tabular MDP, so it is not quite difficult, but we can make it difficult. How do we do that? So first, we used a one hot vector to denote what is the position of the current agent. And then we augment this one hot vector by many noisy entries. And then the observation for our agent is this large dimension vector, of which most of the entries is useless. They're just rubbish. They're just noise, totally Gaussian noise. So the agent needs to figure out which subset of these entries actually has a meaning. It has the meaning of that one hot vector for depicting where is the agent. But if you have a good representation, for example, this one narrow mask, and then by taking the product between these two, and you automatically filters out all these noisy entries. And then solving this MDP is quite simple, because now the input space is just a one hot vector showing where the agent is. But if you don't have this representation, you need large number of samples to know, for example, this entry is actually useless because it has nothing to do with the state and nothing to do with the reward. So we hope to use this environment to investigate and whether a good representation could help to reduce the sample complexity. And actually, we can use this environment to play with it. We can manipulate the kappa and to see whether it really changes, the sample complexity for the target task. How do we do that? So as we say, this MDP actually has a linear representation. So they have one mask. So for linear representation class, we can just choose that dt to be a standard basis over some. For example, we store capital D different observations at a data set, and then the training procedure, that training distribution uniformly sample state from this data set. But remember that in all these capital D different observations, they are essentially just small d different states, real states in this world, in this grid world. So the problem is whether this real position is balanced. For example, in a balanced version, each real position of the agent has approximately capital D over D times. So it just appears roughly the same frequency. But in an unbalanced version, most of these capital D number of observations, they all correspond to the same position in the real world. But or the other position, maybe they just have one observation. So this means if you think about it, kappa, then you uniformly sample from the standard basis, then it is hard for your evaluating process to get a sample from some other states. And so we can manipulate the kappa from small d to capital D. And this is the final graph. The left graph just shows the efficiency of linear representation. So the blue line is you're learning from scratch. And as you can see, it takes about 10,000 number of samples to converge. And if you use a feature function, which you learn from 100,000 samples per task, then you just need around 2,000 number of samples to learn good policy. And if your representation is really good, you use, for example, 1 million number of samples for each task, then you just need several hundreds number of samples to learn good policy. And the figure on the right illustrates the importance of kappa. So if kappa is small, which means the features are balanced, and then you just need several hundreds, maybe 200 and 300 to have a good policy. But if it's unbalanced, which means the kappa is quite large, then the required number of samples to learn good policy is more than 1,000. And this factor is exactly capital D over small d. And this corroborates our theoretical findings. Okay, that's the end. Any questions?
All right, thank you very much.
Oh, I'm so nervous.
So everybody can pose their questions in the chat, but just start things off, I have a question regarding this performance metric that you're using in the end. In particular, that seems to rely on this data distribution dt+1. So I'm just like trying to understand like what is the reasoning behind this performance metric, or can you just go back to its definition? Because you first define your protocol as to, this is how you collect your data, this is how you build your future representation. But here, evaluation on a target task. Right, so here you say that you construct your dt+1.
Yes.
And then you draw a bunch of samples, and then you perform this. But then I guess what I'm not understanding is like, what is really the final metric with which you evaluate this policy?
Final metric.
Mm-hmm.
Our metric for this kappa is how much of the samples is required for you to learn a good policy with respect to some specific kappa.
Okay. So the performance metric that you have in the end is like the policy suboptimality.
Yes, is the required number of samples for you to learn a very small suboptimality policy.
Right.
The convergence rate. Yeah.
Yeah, because like one alternative that I would think about is to say that, okay, that was this kind of like representation learning phase where you have like a bunch of tasks, and then you just spit out in the end a feature vector, right? A feature representation. And then in the test phase, you say that, okay, here's another task. And then you just say, try to minimize your regret on this task. You have like, I don't know, like n episodes of this task. How do you perform on this? So how do you think that your feature representation would perform on this?
Actually,
yeah, so it's different. It's different from yours in the sense that here the evaluation does not feature like some data distribution that you get to design, but rather you want to minimize your regret while learning in this final task. I'm just wondering if you would get something that is comparable to like the standard linear MDP guarantees that you would get if you already knew the feature. The truth.
Actually, for this this red line, you use the phi, which is learned from 1 million samples per task. It is almost perfect phi. So it reaches the almost optimal sample complexity for this task.
Yeah, I was wondering a little bit about like what sort of theoretical results would you be able to show if you would consider regret minimization with this finally produced phi hat. Would you be able to guarantee that you get near optimal errors? Yeah, I don't know. I guess I'm just being too speculative here.
Yeah, actually, I still don't get your point. What is the question that you want to ask? What is the point that you're confused about?
Yeah, it's a bit of a far out question. It's like, yeah, it's nice that you did this. Why didn't you do that other thing? Yeah, we can get back to this later. So maybe somebody has like a less crazy question.
Yeah, Kamir had a question. I think Kamir, do you want to ask your question?
Yeah, sure. There's an assumption here that B is a orthonormal matrix, right?
You mean the linear repetition class?
Yeah.
Okay.
And how crucial is that assumption? Like, if I have general B, you get a bilinear setting. How that can go?
Actually, it is not that important. Of course, you can just take the SVD and you take the small d top right vector for that decomposition. You automatically get this B. Actually, in linear representation class, you can just what you really optimize is the product between this B and the W, which is actually just a capital D dimensional vector because you're learning a repetition, you're learning a regression problem, and then you have a bunch of capital D vector, which is capital D, capital T. Yes, you have capital T number of capital D dimensional vector. And then you take the SVD decomposition and you choose the small d top right vector. And that is what you exactly do, you really do in the optimization procedure. I don't know whether I answer your question or not.
I think you're muted.
Oh,
Come here. You're muted if you're answering.
no, I'm
okay. Sorry. Yeah, it seems I was muted. So if I was wondering whether this sample complexity guarantees you have carries to that setting, or you need this significantly more samples.
You mean if I change this function class to be not orthogonal, whether it will increase the number of samples?
Yes.
Actually not. Because in the real optimization procedure, you never optimize that large matrix, which is capital D times D. You just learn capital D vector. Because you are, if you remember, you do a bi-level optimization on this phi and w. But if you plug in this phi to be b transpose x, and actually this is x bw. So you can just take the product of these bw. So you just take you just optimize over this capital D dimensional vector. You never deal with this real matrix, the large size matrix. And this large size matrix is reconstructed after you get capital D number of this BW, and then you use SVD to reconstruct this B. So it doesn't matter.
It's extra degrees of freedom that you don't need.
Yes. The reason that I assume that the orthogonal is just for the sake of the simplicity when I'm doing the theoretical analysis, but actually for the learning procedure, you don't need to restrict that degree of freedom.
This makes sense to me.
So is it okay if I ask a question, Rui? This is Gugan here.
Yeah, go ahead.
Yeah, so can you just go to the initial slides where you had a bunch of assumptions? In particular, you had made this assumption of this transition probability matrix and the reward function, right?
Yes.
Yeah, right at the beginning where you had defined this linear MDP model.
Okay. Here.
Yeah, here. So here, I mean, in some sense, what you're assuming is that this transition probability matrix and this reward function are some linear combination of the same feature vectors.
Yes.
Right. So, I mean, can you somehow motivate why this assumption makes sense, right? Because this transition probability matrix and reward function in some sense are two different entities, right? So why they should lie in the same, subspace is not clear to me.
Okay, this is a good question. Actually, it also takes me some time to understand, for example, to get a concrete example for linear MDP. Well, there is a very famous conclusion that is, any tabular MDP is essentially a linear MDP. So you can consider this. You can consider this phi function to be a simple one-hot vector function. That vectorization procedure to be a one-hot procedure. So you get a state S and the state and action A, and we're assuming it is tabular MDP, so both of them are discrete. So then you get the input. I don't know whether I can draw it. So your vectorization procedure just outputs S times A vector, and it is one hot. So if this is 1, it means I choose some specific state and use some specific action. And then your phi action just do nothing. Your phi action just output this vector. And then you know why it is a linear MDP, because now theta can just assign the corresponding reward in the corresponding entry. For example, this SA, so I put the corresponding RSA here. And for the psi S prime is actually the collection of all the possible combination of the state and action that can transmit, can go to this S prime. And this position is just the probability of S and A, which goes to S prime. So if in the transition dynamics, the state S and action A can really possibly goes to this S prime, and then you take the dot product between this one hot vector and this corresponding psi S prime, and then the product will give you the transition dynamics.
I mean, you use some word one hot vector. I'm not sure if I understand. Can you, maybe there is some...
One hot vector means there is only one entry in this vector to be one, exactly one, and all the rest are 0.
Okay. And you require that this be true for every phi s comma a, or?
Yes, every state and action.
For every state and action, you require that. Oh, okay. I see what you're saying. Thank you.
So this is a very concrete example about what linear MDP is. And I can give you a concrete construction for what theta and phi, psi, and what psi is.
So if there is no more question, can I ask one more question? I mean, if others don't have any more.
I'm fine.
Yeah, so can you go to that slide of your main result where you had this norm of V pi and V pi star, right?
V pi and V pi star.
Yeah, so you had this
Yes.
distance, right? So you said that there is this little n which somehow looks at the training part, and this capital N which looks at, or maybe little n looks at the testing part and capital N looks at the training part.
Yes.
Right?
Yeah. Right.
So I'm not sure if I understand what that part means, right? Because in general, in the way I look at reinforcement learning is you get data and you would like to somehow get hold of this optimal policy, right? So I'm not sure if I understand what do you mean by some part is used for in that, like what is this decomposition into the training and testing part? So can you please elaborate a bit on that? Thank you.
So your problem is why this bound consists of two parts, and one related to the training and one related to the test, right? Is that what you want to ask?
Yeah, that is the question. Yes.
That is the question. Okay,
so maybe I'm not familiar with this way of writing results or this way of looking at things. So that's the question. Okay.
Because this is actually just an upper bound. So it means that if your number of samples for learning a representation is large enough, then we know just a small number of samples for the target task can guarantee a good result. But if your number of training samples is not that much, so then this part will be maybe a little larger. So the upper bound of this become less useful. So it just the summation for these two terms just tells you that if your reputation is not that good, you may take more effort in evaluating it in the TASIC task. And actually, that is what we see in our in our experiments. So if you use less samples of the less number of samples to learn the reputation, and then you will use more samples in the target task to find a good policy.
Okay, that was helpful. Thank you.
Okay.